Want to welcome everybody to this week's Friday Forum. Well, we filled up the stage again here. Good, good. So the fusion project you will learn about today is absolutely earth-shattering news. Absolutely. Scientists have struggled for many decades to harness fusion power, but on December 5th of last year, for the first time in history, scientists from the Lawrence Livermore National Lab joined other scientists from around the world to use the nuclear ignition facility to prove that nuclear fusion with a net energy gain is possible. As you saw from your catalog, originally this presentation was to feature Dr. Tammy Ma, up here somewhere, who leads the inertial fusion energy effort at the lab. But she was called away to a higher power, you might say, in Europe this week. Oh, I know, pretty bad, huh? Even he's groaning, I know. Okay, today we have the distinct honor of introducing Dr. Scott Wilks, who has been a research scientist at the Lawrence Livermore National Lab for the last 30 years. And in 2006, he received an award for excellence in plasma physics research, way beyond my marine biology background, on an advanced laser fusion concept called fast ignition. And his research has garnered over 17,000 citations. That's way up there, placing him in the top 2% of the most cited researchers in his field. Pretty incredible. He has also been intimately involved in the ongoing success of this project. And so listen carefully today, as this project could be the beginning of the solution to provide clean and abundant energy for the Earth. As a climate scientist, I choke up when I just think about this stuff. I know we're all anxious to hear from Scott, so will you welcome him and thank him for being here?
Thanks, Tom. That was a great introduction, and wow, what a crowd. I did not expect this. Pretty impressive. Exactly. More out there. Great. Wonderful. Well, I'm glad because I love talking about this topic, and Tammy knows it. She is sorry that she's not here, but I think, let's see, let's see. That's going to work. Okay. Yeah, sorry she's not here, but she knew that I love giving these kinds of talks, and so she elected me to be the person to come out and talk to you. So, okay, so Tom did a great job introducing the project that I'll be talking about today. About 10 months ago, the National Ignition Facility at Livermore made headlines around the world, and you went anywhere on online media, you would see these articles that talked about how the lab achieved nuclear fusion breakthrough with laser fusion, and we got target gain greater than 1. How many of you remember that? Wow, what an alert and cognizant bunch. It's great. So what I'll do, the goal of this talk is to attempt to explain exactly what happened and why this result will likely go down in history as one of the major scientific achievements of the 21st century. Like Tom said, December 5th, 2022, we conducted the first controlled fusion experiment in history that produced more energy from fusion than the energy that was put into the target. If you look at this target, this is our target. It's a little cylinder, gold cylinder with a little capsule in it that's filled with, we'll talk a lot about this. It's filled with the fuel, it's deuterium and tritium. But you can see that there are a lot of lasers. These purple things are lasers going in. We have 192 lasers at NIF, and the lasers go in to this target, and that amount of energy that we put in is 2 megajoules. Now don't worry about the unit of energy. We'll talk about that on the next slide. But for now, just think you put 2 units of energy, laser energy, into the target. And this is a plot of the amount of energy that came out. So these are all very distinct shots. And you can see that for a long time, from 2011, when NIF was turned on, there was not much coming out. In fact, the bar is so small, you can't even see it. And so you might think that we were kind of frustrated at that time, and you'd be right. We were frustrated. However, as time went on, we learned about, what to do and what was going wrong, and we corrected for it and continued to do that. And then pretty soon you see this is a very important milestone achievement as well. But then we shot a little more, and then pretty soon we actually got 3 units, megajoules, out when we put 2 in. And so this target was sitting there, 2 megajoules of energy went out, and then 3 megajoules came out of fusion energy. And that was the first time in history that you got more out in fusion energy than you put into your target. Okay, so what is a megajoule? Well, you're probably more familiar with the kilowatt hour, like that's on your PG&E bill. And that's kind of a unit of energy. And that is the energy delivered by 1 kilowatt of power for 1 hour. And that is equal to 3.6 megajoules, which is kind of the amount of energy that we produce with fusion, 3.6 megajoules. Okay, 2 megajoules, just to give you an idea, is the amount of energy that we produced on our best target. I'm talking about one shot. We had a couple even better shots that I won't be talking about too much today. But what you can do with 2 megajoules is you can drive an electric car for about 2 miles. So you're getting a sense of how much energy that we're talking about here. Another way to think about megajoules is in 2020, the average household in the United States consumed about 890 kilowatt hours per month, or about 3,000 megajoules. We'll call that 3 gigajoules. And remember that number, because this is going to come up later in the talk, this 3 gigajoule number, okay? And it's the amount that an average household kind of uses per month. Okay, so just to get everyone on the same page, I'd like to start and talk a little bit about some basics with respect to nuclear fusion. And we're going to start with the 3 most important building blocks of matter: the electron, which is a negatively charged particle, the proton, which is 2,000 times roughly more massive than the electron, and it's positively charged, and the neutron, which is about the same mass as the proton, except it's in neutral. It has no charge. So we can create atoms with these, as most of you know, and I'm going to use the Bohr representation. It's not really looking like planets circling a sun, but this is just for easy cartoon purposes. So this is hydrogen. It's the simplest atom you can make. It's a proton with 1 electron. We're also going to be talking a lot today about something called deuterium, which is, you find deuterium 1 out of about every 5,000 H2O in the seawater is not H2O, but D2O. So it's very plentiful. It's all over the world, in all the oceans. And it is a proton with a neutron stuck in there with an electron. Remember, the proton and the electron equalize each other out with respect to the electric charge. And we're also going to talk a lot about tritium, which is a proton with 2 neutrons in the nucleus and 1 electron around it. And then finally, we'll talk about helium as well, which is 2 protons and 2 neutrons. And of course, because we have 2 protons, we have to have 2 electrons to make it charge neutral. Okay, so I'll also refer to hydrogen sometimes as P for proton, or hydrogen 1. Sometimes deuterium will be called D, or hydrogen. Did I say helium 1? I meant hydrogen 1. I'll also say deuterium is hydrogen 2. Tritium is T, or hydrogen 3, and helium, I might say helium 4 by accident. Okay, so the 2 ways that nuclear energy can be harvested from atoms, there are 2 ways. The first is fission, and this is the one that right now our nuclear power plants are based on. And that's where you have, you take a very energetic neutron and you slam it into a very large, kind of almost unstable atom like uranium or plutonium. And then what you do is that extra neutron kind of makes the thing kind of wobble, and then it breaks apart. And it breaks apart into 2 pretty nasty radionuclides that you really don't want to have around. And they're emitting very dangerous radiation. But you got a lot of energy out when you did that. When that atom kind of split, you got a lot of energy out in the form of these neutrons and the form of these daughter nuclides. So in fusion, what we do is we take deuterium and tritium and we force them together to create helium, And so basically that also gives off a lot of energy. There's a little extra energy left over, and it's spit out in the form of a neutron, and that helium nucleus also has a lot of energy. So there's a certain amount of energy that goes in. For example, in fission, it's the neutron that you had to kind of give it energy and to give that big atom energy. In fusion, you kind of have to move these things around. They have to be pretty fast to kind of go together, and we'll talk about that in detail. And so there's some amount of energy in, but then there's a lot of energy that comes out once you get once you play with the nucleus to some extent, you get energy out. Now, it turns out that the energy out versus the energy in, the energy out is much, much greater, okay? In fact, both of these nuclear reactions release about 10 million times more energy than burning the equivalent amount of coal. So it's an incredibly efficient thing, and you can only imagine why people were so excited to, find this nuclear energy and try to harness it. And we'll talk more about fission, but mostly from now on, we're focusing on fusion. You can see that fission has these nasty outputs that you have to deal with, whereas fusion, you make helium. Okay, so how does nuclear fusion work? Let's consider two protons, and let's try to put them together. Well, if we just take them and they don't have much energy and we try to put them together, they will repel because like charges tend to repel under normal conditions, okay? But it turns out that if they're sufficiently energetic, if we can figure out a way to make those protons really moving quite fast and hit each other, then it turns out that they will actually stick together and become attracting due to the strong nuclear force. And so that is kind of that's the basis of fusion. And what we do is we fuse deuterium and tritium together, like I said, to form helium. Now, what happens there is if you consider the amount of mass that's in the deuterium and tritium that you started with, and then you went and measured the amount of mass that's in this neutron and this helium nucleus that you're left with, you would find that there's some missing mass. There's more mass that you started with more mass and you're left with less. Well, that extra mass got converted into energy through Einstein's famous E = mc² equation. And so that's where all that massive amount of energy comes from. A little bit of mass goes a long way when it comes to the energy. Okay, so the question now is, well, how energetic does this have to be? And it turns out the answer is, how energetic do these deuterium and tritium have to be in order for fusion to occur? And it turns out that fusion requires it to be really hot, okay? You need to be in what's called a hot dense matter that's called plasma, okay? You have to be in a plasma state. Okay, so what's a plasma? Well, first, we need to understand what is a gas, okay? Let's talk about a gas first. It's a little more relatable. Imagine a scuba diver and they've got a scuba tank on their back, and the scuba tank is filled with air, and the air molecules are kind of bouncing around. Now, we have a box of deuterium instead of air, but you can see that what's happening is the deuteriums are kind of bouncing around. They bounce off the container and they kind of bounce off each other. And so this is kind of what a gas is. It's just kind of, something that's sitting there in a bottle. Okay. Now, a plasma is kind of like that gas, except the atoms are ionized. And what I mean by ionization is that you heat the gas so much that you rip the electrons off of that nucleus. And so now they're free, they're just flying around at random. The nucleus is by itself, and now that's charged. The electron is also charged. So now they're interacting not through collisions, but through electric and magnetic fields. And so it's very complex motion. But basically, they're moving around all at random, okay? And so this is kind of what a plasma is. A little more complicated, but basically this is kind of gets you the idea of what a plasma is. And now we had to really heat this high, and we have to compress it in order for fusion to occur. But the important thing is it has to be in a plasma state. So what are the requirements on the plasma for ignition and burn to occur? Okay, so first, like I say, you have to confine this plasma at a high temperature. Has to be really hot so they get together, and you have to do it at a required density. If it's just a few in a box, they're rarely will they meet, and so it has to be dense enough so that you have a pretty good probability of them colliding, and you have to do it for a certain amount of time, because if you don't do it long enough, it's kind of like when you try to start a fire. You can't just kind of like take one match and then just kind of just show it to the wood and walk away. You've got to, you kind of got to take some time and get the stuff started. And a plasma ignites and burns if the fusion reactions produce enough power to maintain the temperature without external heating. So for example, with that fire analogy, once you kind of do get the wood going, you take that match away and the wood continues to burn. That's a plasma ignites and burns like that. You're not putting any external energy in, it's burning by itself. That is the thing that had never been done before. And that's the thing that we did. And so with fusion energy. So you might say, well, what are the numbers associated with the temperature and the density and the times? Well, it turns out that J.D. Lawson, this physicist from England in 1957, wrote down a criteria that said the product of the density and the temperature and the confinement time has to be greater than this number that he wrote down. And it turns out that in fact, is the requirement that you need to achieve thermonuclear ignition and burn. And it turned out that an earlier historic shot that we did August 8th, 2021, actually satisfied Lawson's criteria. Okay, we got ignition, but it didn't have net energy gain. It didn't go above, it wasn't more energy out than we put in with the laser, so it wasn't quite as flashy. But in principle, we'd already broken Lawson's criteria for the first time. Okay, so there are two main approaches for confining plasmas to try and make reactor scale fusion. Okay, there's magnetic confinement. Has anyone heard of magnetic confinement before? Okay, good. So it turns out that is using magnetic fields. You can try to make this kind of torus or donut shaped plasma. And that was the original one. That was about 70 plus years ago. People had been working on that for that long. And that one, they take the tack that, okay, look, what we're going to do is we're going to have lower densities and high temperatures, but we're going to do it for a long confinement time, like seconds or minutes, okay? What we're doing with inertial confinement fusion is we're taking the tack that we're going to say, hey, you know what? We're going to do it for extremely high densities and high temperatures, but we're going to do it for a very short time. And we'll talk about how short a time in just a minute. But what we do is we take 192 laser beams, all directed at a tiny centimeter-sized target that you saw earlier, and you can't see it in this little white glare. So I'll blow it up a little, and so our target is sitting in the can. Okay, so I'm not going to show the can right now. We'll talk about that later. But for now, this is the pellet that contains the blue DT fuel, the deuterium tritium fuel, and there's a little skin around it that's made up of either plastic or high-density carbon that I'll call the ablator, and that gets burned away and crushes. That basically gets burned away. We burn that away, and then as that gets blown away, it forces, by Newton's third law, it kind of crushes the inside and crushes the fuel, gets it hot and dense, and that's kind of what we want. We'll talk about that in a little more. Oh, and by the way, we've been doing inertial confinement fusion for about 50 plus years. Okay, so like I say, laser fusion was the first to demonstrate target gain. And if we go to a plot of Lawson's criteria, what he said you needed to get to, this is the density and the confinement time and the temperature down here. You can see that magnetic fusion is kind of right here, and they have to get to a slightly different Lawson criteria, but they have to get to this green line, and they're still working on that. But you can see where NIF, the National Research Facility at Livermore, we were shooting for a long time. We were very close, but then we tweaked something. And if you're interested in the question and answer, I can talk more about what that was. But we actually figured out ways to get above that black line there that represents Lawson's criteria. Remember, he said you have to have it above a certain value. Well, that's the value, and we got above it. And that's why people were writing all those articles and what was happening. This is exactly why it's such a big deal, because people have been struggling, as you can see, the grayed out area here. This is mostly magnetic fusion. They've been trying for 70 plus years, and they're gradually kind of getting up to there. And then suddenly, in some sense, we're the upstart, the 50 years, 50 years only, kind of ended up getting it. So it was kind of a cool thing. I have to say, I had worked on it for 30 years and they'd already been working on it for 20 years. And I was, is this really going to happen? I mean, this is really a difficult thing. And so it's just so satisfying and rewarding to see it happen. Again, I'm a part of a very, very large team of thousands of people across not only the lab and not only the US, but across the whole world that actually contributed and made this a really exceptional achievement. So it's kind of one of those things that, you just can't have a couple smart guys in a room doing. I mean, you need this massive amount of people doing all different types of things from, at all different scales. It was really a wonderful, wonderful thing. This is just a blow up of that corner there where you can actually see us crossing that Lawson criteria. Okay, so fusion is a pretty cool way to make energy, as I hope I'm telling you. Or convincing you. In fact, stars do it. This is how vast majority of the energy in the currently in the universe is made, is through fusion in stars. And how does the star do it? It doesn't use magnetic confinement. It doesn't use inertial fusion. It doesn't use inertial confinement. It uses gravitational confinement. Stars are so massive. They have so much mass that the plasma just stays there because of the gravitation. It's all just attracted to it. And so that's how a star is able to keep remember that Lawson criteria was density, temperature, and confinement time. Well, the sun has billions of years confinement time, has no problems at all, has forever. We use inertial confinement fusion, and remember, it's the inertia when the outside skin, that gold skin, kind of blows out, then the inside fuel crushes, and it's the fact that it was moving in, it's the inertia of itself that keeps it kind of together, and then once it burns, it explodes. So it's a very, very short thing. We'll talk about how long. So what we do is we have this, like I said, we have this cylinder. It's a gold cylinder, and inside it we place our fuel. And here's the fuel. That's how big the fuel is. And so if you see this picture, so this picture here is at the actual laser facility, and it's 3 football fields big. That's how big it is. And this is a chamber, and I'll show you the scale of the chamber in a minute. But that chamber goes in there, and this is the actual target. And so we have this laser that's 3 football fields big, and we put all the energy into this tiny little thing. Isn't that incredible? Okay, so and that's the pellet imploding. Okay, and now the star, like I say, giant plasma, long confinement time. We have a tiny plasma, short confinement time. We'll talk about that in a minute. Okay, so how does a star fuse? Okay, we already talked about how we do it. We do it with deuterium and tritium, right? How does a star actually fuse? Well, what it does is, in essence, it takes 4 protons. I'm pointing to my screen. That doesn't help. Yeah. Okay. This is the so you can see my cursor. Okay. Great. Okay. So here you can see that basically what the star does is it starts with 4 protons deep in the core of the sun at about 2 kilovolts. And what it does in temperature, and what it does is it essentially goes through a couple different steps of fusion, and then it ends up with a helium nucleus. Now that's kind of interesting, isn't it? You started with 4 protons and you ended up with 2 protons and 2 neutrons. That's pretty amazing, isn't it? Well, because during one of those steps, it turns out that one of those protons is converted to a neutron. And it does that, of course, the proton's positively charged, and the way that it gets rid of its charge is it ejects a positron, which is kind of like an electron, but it's positively charged. It ejects that and a neutrino, and then you've changed one of the protons into a neutron. Isn't that amazing? Who needs science fiction? That's amazing. By the way, the neutrino is kind of interesting. You know, the energy when the sun burns, it's burning its energy at the core, but it takes about 10 or 100,000 years for that energy to actually make its way out to the surface of the sun for us to actually use it. And so you could think about, well, what if the core of the sun stopped burning? We wouldn't know about it for 10 or 100,000 years. So it may, people kind of started worrying about that, right, at some point. And but it turns out that because of this interaction where the proton turns into a neutron, that neutrino is given off. It's virtually a massless particle, and it goes through everything, and it goes through the sun, no problem. In fact, there are plenty of them going through us right now. But the solar neutrinos, because we can measure them, we know that this fusion is occurring in the core of the sun because those neutrinos are coming out. So that's kind of a cool side note. Okay, and then like I say, we use deuterium and tritium. Interestingly enough, we also make helium, but we kind of stack the deck. You see, we don't ask this thing where a proton becomes a neutron takes a very long time. I mean, like, hundreds of thousands of years or more. But and the sun's got time, but we don't, and we have to do it quickly. So we throw in some neutrons and make it a little easier for the fusion reaction. Okay, so how does it work? How does NIF work? Okay, what we do is, like I say, the lasers go in top and bottom. We split the beams. We put half in the top, half in the bottom. Now they don't hit the target. They don't hit the pellet. They hit another part of the target. They hit the cylinder, the gold cylinder that's sitting there, and the target's sitting in that. Okay, so and when the lasers come in and they hit that wall, what they do is they create X-rays. And those X-rays, now what we've done is, in essence, we've created like an X-ray oven. Instead of a microwave oven, we've created an X-ray oven. And what that X-ray oven does is, remember that told you that there was a skin over the deuterium tritium fuel? Well, that skin gets super hot from those X-rays and it explodes. And when it explodes, it crushes the fuel and heats the fuel. And that's what happens once that gets crushed. Then you get incredible pressures, in this case, 500 billion atmospheres of pressure. And that's enough to actually get the fusions to start occurring. And then we turn off the laser, and then the thing can go off and burn, spreads and burns. And that's kind of how fusion works for laser fusion. Now, the question is, how short is this whole process? Okay, so in order to get that across, let's do a demonstration. What I'd like everyone to do is, at the count of 3, I want everyone to blink. And when you blink, just do a normal blink. Don't do it too fast. Don't do it too slow. And I want you to blink and then kind of be cognizant of how long that took. Okay. 1, 2, 3, blink. Okay. Everybody kind of see roughly how long a blink is. Okay. Turns out that it's a 1/10 of a second. Okay. So it turns out that the entire process that I've just described, including the lasers coming in, the thing blowing up and then burning and everything, it takes 1/1,000,000th of the time it took you to blink. That's how quick this is. Okay, so that's part of one of the beauties of laser fusion is that this is not something that's gonna kind of unstable and it's gonna burn forever. I mean, this is kind of this happens and it's done. Okay, the second question is, how big of a laser do you need in order to do it? Okay, well, 2 things. One is, remember the Lawson criteria: density, temperature. You need to get big enough laser so that you get to the required temperatures. Okay, so I'm sure that many of you remember when you were a kid and you would go out with a magnifying glass and you would try to, get just the right focus so that you could burn some leaves. Yeah, I see a lot of heads nodding. This is great. Well, you were using 2 watts of sunlight and you were getting to about 100 watts per square centimeter is what you were getting. You were getting to 300 degrees Celsius. It turns out that what NIF does, in order to get the 10 kilovolts of energy, which is about 5 times what the core of the sun is, by the way, in order to get the temperatures we need, we have to have over 100 trillion watts of laser power. And so it's 400 terawatts of laser power that we need to get to the temperatures required. And those temperatures you can see, so 10 kilovolts is kind of here, this 10 kilovolt here. And so you can see that this DT, deuterium tritium, this is the higher up on this curve, the better you are, because this is the nuclear reactions that you get per volume per time is related to this number. And the bigger the number you get, the more nuclear reactions you get. That's what you want. And so you can see why we use DT and not deuterium, say. That's why we put in the tritium. It makes it a little easier. In fact, it makes it orders of magnitude easier. Okay. So essentially, we need temperatures of about 5 times hotter than the sun, and we get it. Okay, and big enough the laser also has to be big enough to reach the density conditions that are required, because we have to remember we have to have that skin blow off and crush the fuel. And how much do we crush the fuel? Well, imagine, so like I say, our fuel is a 2 millimeter diameter pellet. It's pretty small. We put this giant laser on this poor pellet. The energy from the laser, we don't shine the laser directly on it. We do indirect drive. The pellet is 2 millimeters in diameter. Now imagine if that 2 millimeters was an analog of a basketball, okay, basketball size. How much do we compress it? We compress it about down to the size literally of a pea. 50 micron diameter, which is the diameter of a human hair. So we have this 3 football field long laser that is actually, compressing something to the size of a human hair. Pretty remarkable. Okay, so, and when we do this, the deuterium tritium fuel densities get to about 1,000 times solid density. That's what we need to satisfy the Lawson criteria. Okay, so you might think, well, who came up with this crazy idea? Who would even think to do that? Well, it turns out John Nuckolls did in 1972. He wrote a paper which proposed to try these thermonuclear microfusion explosions with lasers. At the time, people were doing actual uncontrolled thermonuclear explosions, and we were doing it in a Nevada test site. And that's what you see here is just a bunch of craters from a lot of nuclear tests. And so John had the idea, hey, why don't maybe we can do this on a small level. We can do it on a controlled way instead of this uncontrolled thing. By the way, remember that 3 gigajoule that every house uses per month. 1 ton, okay, is just another energy unit. 1 ton is about 4.2 gigajoules. So that's even more than the amount that one house uses for 1 month. And it turns out that each of these tests were anywhere between 10 and 100,000 tons. So you see that the amount of energy that was dealing with is much different than the scale that we're dealing with, was just megajoules. And that's exactly why we think that fusion energy, laser fusion energy, is viable for an energy source, because it's controlled in a controlled fashion, and you can actually harvest that energy. This is just completely you would blow up your power plant every time you got energy. So it's probably not a good idea. So the initial estimates were about a 1 kilojoule laser. It turns out we needed a couple thousand times more of that. But it was great, maybe, that they thought that it only took a kilojoule, because if they knew how much it took, they may not have embarked on this, because it turned, at the time, lasers were about 1 joule. Okay. But they said, well, let's try it. And they built Janus, which was a 10 joule laser. Then they built Shiva, which was a 500 joule laser, and they thought they were getting close. They built Argus, 1 kilojoule, and it didn't happen. Now, to be fair, they kept revising the estimate of how much energy it would need, and we learned a lot every time. And this is a great lesson, is that even if you don't get it initially and it seems hopeless, you just continue to try and learn from when you get something from the experiment. And so it really worked out great. That was fantastic. This was a great progression. So that Argus, we learned a lot. And in fact, enough that we thought we could do a really good job. And we built Nova, which was a 300 kilojoule laser. And now we're talking. That's getting to be some energy. And it turned out that Nova, and that's kind of when I showed up, in like 20 years after they had gone and started. And I showed up around Nova. And then we started working on designing the next laser, and that was the NIF, the National Ignition Facility laser. So all that work culminated with this National Ignition Facility laser effort at Livermore. There's the picture. There's NIF. We talked about this before. This is all the kind of the glass and the optics that the laser requires in order to take it from its little seed laser to the big 192 beams that have a lot of energy, the 2 megajoules that we need. And this is the chamber where the little target sits. So needless to say, it's the biggest and most energetic laser on Earth. There is the target chamber being loaded in when they first built NIF. It's kind of going to the building. This is inside the chamber. You can see Here's some guys on a lift inside of it, and you can see for scale how big the chamber is. This pencil-looking thing from your perspective is really actually, meter in diameter. It's huge, and it kind of comes down to a tiny little point. And at that tiny little point is where we place our little cylinder. And inside the cylinder, we put the tiny little deuterium tritium pellet. And then we turn on the lasers and shoot the walls of that hole realm. We call it the hole realm. We call that cylinder a hole realm. And it creates the X-rays required. Okay, so now I'm going to try and play a little movie of an actual NIF shot starting from when the lasers start going through and becoming amplified. Okay, it's almost like mission control, huh? Okay, so here they go. Okay, so these are the little seed pulses. Now what they did just there was they flashed the flash lamps. So we have to put a lot of energy in the glass because the little seed pulses are coming out right here are going to take out all the energy that we put in that glass. We just flashed that glass, and now it's just sitting there waiting for these little seed pulses to go by and subtract and take the energy out from the glass and put it in the little laser pulses right here. These are our 10 nanosecond pulses that are going through. They got it amplified right there and right there. And now they're getting conditioned as they go back and forth. Every time they go through, they gain in energy. So they come out, they start with a nanojoule of energy and they end with a megajoule. So we're talking, several orders of magnitude energy that gain. Now we're going along in the beam tubes. I think they've got the majority of energy that they're going to get, and now they're heading to the chamber. You can kind of see the chamber over there in that blue, and half the beams are going to go up. Now you notice they're red. We do this all in 1 micron light, in red light, but then we realized when we were doing Shiva that we needed to change that, not from red light, but we needed blue light. So we have crystals that change it from green to blue, and then we use blue light. Now it's going into that little, the little target, the hole realm. And you can see that they're going to show, okay, so now this is billionth of a second. So this is nanoseconds. And you can see as time goes on, there's more and more X-rays created off the wall. And now that skin of that plastic or that high density carbon is now going to explode off as it does. And now it's compressing the fuel inside and we got fusion. That's it. Yeah, I'm glad you like that movie. Yeah, somebody did a great job on it, not me. Okay, so this result demonstrated the scientific basis for laser fusion as a potential energy source for the future. Now, a lot of people who know, something about this, they say, wait a minute. NIF used, yeah, sure, you put two megajoules of laser energy into that target and you got 3 out. That looks good, but didn't it take you a lot of energy to make that 2 megajoules of energy for the 2 megajoules of laser energy? And the answer is yes. It took 477 megajoules, in fact, to make through this 3 megajoule output. And so you might think, well, that's a JIP. But the thing is, and it's true, the energy out was only 3 megajoules. The energy in was 477. So it's like 0.6% efficiency. It's like, boy, you're not going to be making any power plants with that. Okay, and that's true. We're not. But the thing is what you have to remember is that we were not trying. Livermore is an NNSA facility, and our basic main mission is to understand and ensure that our stockpile of nuclear weapons is safe and secure, and we understand all the physics behind them. And instead of doing the tests in the Nevada test site that you saw, we try to do as much physics on these fusion devices that are making neutrons as we can, because that allows us to not have to test. And so that's kind of what we were doing, is we were trying to build the biggest neutron generator from using fusion that we could. And we did. Now, why? And we were not trying to make power. We were not trying to make net power. We were just simply trying to make a lot of neutrons and study the fusion process. And we, at the time in the 1990s, when we started thinking about designing NIF, we said, okay, what we're going to do is we're going to take the safest laser technology that we can use, and it was glass at the time. And we're going to use that, even though it's extremely inefficient. And there were, at the time, there were diode lasers that existed that were more like 10% efficient. And, that would have been a lot better number than, it would have been 30 megajoules instead of 3, right? It would have been great. But the thing is we wanted to guarantee it would work. Okay. We couldn't bank on like, well, there's this technology that might work. I mean, we had to use tried and true technology, which was really like, 60s or 70s technology that we designed in, or maybe even 80s into the 90s when we did the design for the NIF. So that's why it's not good for producing energy. Okay. So, well, why do we think we can use laser as a clean energy source for the future? 2 reasons. One is, like I told you, NIF is an extremely inefficient lasers, but new lasers are coming online now that are like 15 to 20% wall plug efficiency. You just plug them in and you get that much. So that immediately helps you go from like 477 megajoules to 15 megajoules. That's looking pretty good. In addition, we think we can get much better target gain. As you saw from that earlier picture, we're really learning how to do this. You saw that for 10 years, we got nothing. And we just now have started getting gain, and we're learning rapidly. We've already repeated this these types of shots like a handful of times already, like 4 or 5 times. So we're really starting to learn, and we have designs. Here's a couple shots, for example, that got over break even. But we have designs that can go up higher, and we have designs that can even novel ideas for fusion that can actually get us to much higher gains. So 100 times. So instead of like the 1.5 or whatever gains we're getting now, we could get maybe 100. And so if you put all those things together, both of those things together, you could actually quite easily get like 600% efficiency. And so that's why we think for the future, this is certainly something that could be looked at. So, for example, keep in mind, NIF was actually just built to demonstrate, number one, it was built for doing stockpile stewardship work, but it was also to demonstrate that break even could be achieved. And so you think of the Wright brothers, okay? The first plane, probably went, a couple hundred or maybe 100 yards and probably got off the ground, 6 or 10 feet or something, right? I mean, everyone didn't stand around and say, well, I don't see you going to Europe. Right. I mean, that's kind of where we are. Right. I mean, we're kind of this is baby steps, and we're at the beginning, and it's a pretty exciting thing. So, and I think and the important thing is that we showed that a laboratory thermonuclear explosion can achieve target gain of greater than 1. That's scientifically, we showed that it could be done. That was the key thing. Okay. Why does fusion energy look attractive as a clean and limited energy source? Well, Tom was talking earlier, lamenting the fact about the carbon emissions when you burn coal and fossil fuels and so on. And you can see that that's a tremendous amount of the energy in terawatt hours per year that we're using in the US. There's nuclear. You see that nuclear is kind of capped out. It's probably going to go down. Of course, solar and wind are picking up, but those are kind of geography dependent fuels. This would be an unlimited geography independent fuel. As I mentioned before, deuterium is found all over all of the oceans. You basically breed tritium from lithium at the site itself. We don't need to talk about that detail unless you want. There are no emissions or global warming like there are for the carbon based. There's no long-lived radioactive byproducts. The other nuclear fission seems like a good idea, but you have this issue with the long-lived radioactive byproducts. There's no proliferation of fissile material. You're not using uranium or plutonium as your fuel. You're simply making hydrogen. And there's no runaway chain reaction possible. In fission, you're kind of like using the radioactivity. You're almost kind of like, you're right on the edge. It's a little. It requires this delicate balance, right? Of, you don't want to, you want to make enough heat to boil the water for the turbines, the gas for the turbines, the steam for the turbines, but you don't want to blow it up. And so it's a very delicate balance you have to walk, and you can see that there's lots of room for error. And so there was the 3 Mile Island. You see that U.S. was just exponentially building these things, and it looked really good. But then 3 Mile Island occurred, and they said, well, wait a minute, we better slow down. And that kind of put a damper. Then there was Chernobyl that put another damper on us, and especially Germany. And then Fukushima, it just keeps occurring. And, Fukushima, this Japanese took a big hit in the amount of energy they were getting from fusion because of their accident. So, people are looking for something else, and fusion may well be that clean energy source for the future. So as I talked about earlier, NIF, again, it was built to kind of be a demo and also to do work for the mission of the laboratory. And it only shoots, it says here it shoots once every 8 hours, but not these kinds of shots, these ignition shots. They're very boutique. Okay, they take a lot of work, they take a lot of preparation, and they maybe they shoot every so often, not maybe once a month or something. And now, whereas if you were to try to say, well, okay, let's try to imagine that we do want a fusion power plant. We want to build a fusion power plant. Well, what you would have to do is you would have to have something like NIF go off, but you would have to have it doing it 10 times a second. So it takes it's an incredible. And why don't we shoot NIF more often? Well, the reason is remember when the glass got flashed and we kind of stored the energy in there, and then the lasers came by and picked them up. Well, those things, they get hot and they had to take a long time to cool down. So you can't flash them again or they'll melt. So they have to take a long time to cool down. So you need to come up with completely different laser architecture, and people are starting to work on that now. There's some very exciting new possibilities. And there's new companies that are based on trying to figure out this laser problem. But the laser problem is a big thing. You need a high average power laser, and we do not, these kinds of lasers are not high average power. They're very high peak power, but they shoot, if you average it over a week, it would be like 10 watts, less than a light bulb. So you do have to, that's a huge problem that has to be overcome. There's another problem, and that is, if you're shooting 10 times a second, that means you need 10 targets every second. And if you add that up, that's 864,000 targets a day. That's almost 1 million targets a day that you need. And right now, it probably takes people a month to make one of these targets, and you have to do it with care. There's a team of people that are just kind of shepherding these targets through, because they have to be so just right. It's very impressive. You should have someone come and talk about the NIF target someday. And I can talk in the question and answer. I can say a little bit about that. If you wanted to make a top pilot plant, an IFE, inertial fusion energy plant, you're going to need, this is a big problem that you're going to have to deal with. Okay. And so, wow, great timing. Significant challenges clearly remain. And like I say, mostly the lasers and targets. The good news is that these are technological challenges, not scientific. We've shown that the scientific challenge has already been accomplished. Okay, so is the future already here? Well, there's a proliferation of nuclear fusion startups. There's 30+ private companies pursuing fusion the last time I counted, and they're all over. In fact, some of my friends are startup. They're now business people instead of physicists when I knew them last, which is great. And this is, this new push from the private sector should really speed up the process. I'm really hoping that this really speeds up the process. But in reality, it's going to be decades before any real laser fusion power is put on the grid, just for those reasons that we just talked about. So again, I want to stress that this achievement was built on decades of research by, it's just an incredible team of people across the lab and across the entire community with respect to not only the U.S., but, we had people in France and England and Japan and Germany that were all helping. And it's just been a wonderful thing to interact with all these incredible people and just be a part of this team. Now, I really feel like that is the way you have these kind of achievements occur. So I don't know if you can see it, but in this picture, these people are holding their hands like this. Does anyone know what this is? Somehow I know this crowd probably knows what this is. Okay. So anyway, it turns out that in in 2012, portions of Star Trek Into Darkness were actually filmed at NIF. So now if you go back and look at that, you'll see the actual NIF chamber. Now you'll look at that movie and say, wait a minute, that's the NIF chamber. So anyway, okay, so today we learned, what did we get? Well, we saw that fusion is a nuclear process that powers the sun and all the stars. That using lasers to confine and heat a plasma is one method of achieving fusion on Earth. Fusion ignition is when the fusion energy released is greater than the laser input energy. That this fusion ignition threshold for the first time in history was surpassed with laser fusion. And this demonstrates the scientific basis for considering laser fusion as an energy source. And now we can start to think about credible paths for a clean and unlimited energy source can be built on this result. And that's about it.
Thank you so much. That was fantastic. I'm going to use my bully pulpit
Thank
here to ask the first question. Based on what you were just saying, about 30 corporations are already in the biz of looking at fusion. What does that mean? What are they doing? They can't replicate what your organization has done or all these people from around the world has done. What are they doing, all these other corporations?
That's a great question.
We're going to take questions from the audience too.
That is a fantastic question. So that is a great question. I think, one thing that they can do is, they can leverage private funding that we could otherwise not in the government do. And so there are like kind of, I don't want to say Hail Marys, but I want to say like extremely, exceedingly speculative fusion ideas, that a lot of these companies are based on. And, I mean, no offense, if you guys are listening, I know I worked on one of them early on when it was in discovered. But I think that's I think it's great because basically what we can do now is we can throw a bunch of seeds and kind of see if anything grows. That's kind of the way that I see this. You're right. They're not going to have the compute power. They're not going to have NIF was billions of dollars. Okay. These companies, might get, a couple tens of millions of dollars, maybe 100 million or something. So you're right. They're not going to be building a NIF, but they can make strides and they can make progress and try to push in areas where the lab might think, well, we have a mission and we need to kind of be focused and make sure that we take the tried and true path. Kind of like, the way to look at it is this. The lab would never have thought about like going with a very advanced laser technology when we were designing NIF, right? We stuck with the tried and true and we were not going to take any chances. Well, I think that the company now with this private sector money, what you can do is you can say, well, look, you know what? Let them try and, try some of these things that maybe were a little too risky for the lab to try, and maybe they'll succeed. And then, everyone wins. So I think that's what I see their role as. And I also think they can work with the lab. And then they can also, the labs in some sense also kind of leverage the private investment there, because the labs will be able to help them with all the expertise that kind of lies at the labs, really.
Okay, that's great. I'm going to open it up to questions here and also on the Zoom. Do you have any questions on the Zoom yet? Go ahead.
So this is from Jerry. He wants to know if there's any risk of turning Earth into a mini star.
Is there any risk in turning Earth into a mini star?
Oh, I think it's in jest. I think that I think what he's doing is he's reminding me to say something that I just said in passing, and that is, so for nuclear fission, again, you're kind of, they talk about criticality, right? You're like, it doesn't sound good, and then they have these meltdowns and, this is really dangerous. In laser fusion, you see how hard it is, how hard it is to have happen, number one, that it immediately shuts itself off. It's like, it happens in the blink of an eye and it turns off even faster is the way to look at it. So there's no hope ever of doing that. Yeah, that's right. So I think he wanted me to bring up that it's a big plus when you think about fusion versus fission.
Okay, I see we have someone up in the upper balcony here. Can you hand that down?
Tom, first of all, congratulations for all the work you do on these forums. They're outstanding. And thank you, sir, for an outstanding presentation today.
Welcome.
Kind of think you've only shown us half of the deck of cards because you've spoken entirely about doing it through lasers. And as I understand it, there's an entirely different approach that melts the stuff using magnets with a whole different process. MIT's working on it. A lot of similarities, but not identical. Could you, for us laymen who don't really understand much about this, are there two forms of doing this fusion? And if so, is one form better than the other?
Yeah. I actually mentioned that. Maybe it's worth going over again. Maybe I did it too fast. Yeah, I talked about it. But maybe for your benefit, I'll do it real quick. If you guys don't mind me kind of going through all these animations. Okay, where is it? It was at the beginning. Here we go. Okay, yes, there are two ways to do if you were going to, do this reactor scale fusion. There's magnetic fusion, magnetic confinement, just like what you're mentioning, and yes, so there's in fact there's a lot of private money in going into this too. They're trying to leverage new technologies in magnets. Yeah, so that's one way, and that they use a tokamak and ITER actually. So this is interesting. There is this has been around a lot longer than 20 years longer than inertial fusion has, and so they got a little bit of head start, and so then they are actually building what's called the International Tokamak Experimental Research Reactor or something, and what it is they're going to try to attempt to get more energy out, and they're trying to use it as a reactor. But for a short amount of time. I think there have been a lot of setbacks, and it's a very expensive thing that everyone in the entire world is contributing money to and working on. A lot of scientists from around the world, and the U.S. included. And I think that got pushed back to, I think they're going to start trying to burn DT in like 2035. And again, I'll real quickly mention that a lot of that work that I've grayed out here in this plot has all been magnetic related fusion. Not always tokamaks, but related magnetic based fusion. We're a very kind of odd bird in that we are not having anything to do with, we have something to do with magnetic. The magnetic fields are present, and we kind of have to worry about them, but they're not, they're not principal to our method of making fusion.
Okay, I'm going to use my bully pulpit again. I think with this kind of important technological stuff going on, we're clearly at not at the cutting edge. We're at the bleeding edge of technology here. And the Wright brothers analogy is very clear. I think we ought to take advantage of having Scott here if he's willing to go beyond 4 o'clock and answer more questions if you guys are interested. Are you? Okay, anybody else with a question? Let me know. Let me get down here.
I was curious if the Livermore Laboratory is under the government money?
Yes, we're a government laboratory. Lawrence Livermore National Laboratory. Yeah, we're a government laboratory. Correct.
Okay. The other one is, when you did those experiments in that land, what kind of an impact did it have on the land?
Oh, let's see. I want to actually amend my first answer. We're actually Lawrence. We're actually called LINS now. We're not specifically owned and run by the government, but kind of by private entities. But we do mostly government work, so that's why I feel like we're a government laboratory. The second question is the Nevada test site you're talking about there? Yeah, those craters are there, and they haven't tried to fill them or anything. I don't think the radio is not radioactive anymore, that area or anything. I mean, it was a desert and now it has holes in it. That's how they left it. I don't think anything, yeah. I've been there before. You can take, I don't know if you can, I think you might be able to. I know it's every once in a while people can take tours of it. So, you could go see it.
So which is the bigger problem? Lasers or the targets? I mean, that was a million targets.
Yeah. It's a million targets. And, if you think about, and then targets the targets are just exquisite, incredible. I mean, they have like almost zero defects. They're probably some of the most perfect spheres on the planet. I mean, it's just amazing what they go through. In fact, they have to fill it. I didn't talk about this in detail in the talk, but it turns out that the actual, that skin, that plastic skin I talked about, and then inside I would just say the DT fuel. Well, it turns out that what it really is it's DT gas that they put in there. They have to put in there after they make that skin, and then they cryogenically cool it such that you get a layer of DT ice along the inside of that plastic, and the rest of it's gas that sits there. And so then even when you cool that down cryogenically, you have to have this very smooth inside, and it's just and oh, by the way, so there is, in order to get the gas in, you have to have what's called a fill tube. Okay, so there has to be like a little straw like this. It's kind of going into the capsule, but we can't tolerate. Remember, the basketball kind of got squished to the size of a pea. You can't really tolerate any imperfections on the outside. So even that little tube is a problem. In fact, one of the reasons that we got the result we did was because instead of using a 5-micron diameter fill tube, which is 1/10 the diameter of a human hair, we went to a 2-micron fill tube. So it's just inconceivable what these guys do. So just imagine doing that 1 million times a day perfectly. So there's a lot of issues. I think that's I mean, I don't know what to say. They're both kind of like such orders of magnitude problems that I would think that the target is a little harder. Well, I don't know which is harder, but it's harder to wrap your head around that one. I think the laser one, there are a lot of interesting ideas now floating around about how to make a laser do what it needs to do for and get the high average powers that you need. So they're both, yeah, I wish I could answer. I don't know. They're both so hard. I keep thinking this one, no, that one, no, this one.
Yeah, just real close. Oh, yeah. All right. I can see how lasers would make things hot. And is it just the heat that gives the compression? It's a little clear how it goes from a basketball to a pea.
Oh, okay. So let me go back to this. Oh, here, it's right here. Cool. Okay. Okay. So now imagine that. So this is the skin. Okay. Just imagine this is a piece of plastic. This is plastic. Okay. It's a plastic bubble. Okay. And you've got some fuel in it. Okay. Now, what happens is the lasers really heat up the cylinder. They don't touch this at all. The lasers hit the cylinder that this is sitting in, and it makes X-rays. And so imagine it's like a microwave oven, except they're X-rays. And instead of heating up your food, you're heating up this gold piece. Okay. So now when this gold piece gets heated up, it blows out, right? Kind of like a rocket. When you want to make a rocket go up, there has to be a lot of stuff that gets thrown down, right? Well, what we're doing is we got to throw a lot of stuff out in order for stuff to go in to compress. Does that make sense? Okay, good. That's exactly what happens here is the stuff goes out, and as that goes out, everything else, the fuel inside compresses. Does that help? Okay, great.
All right. Well, I think we need to give you a big hand here for the fantastic presentation.
Well, thank you. It was a wonderful experience, and I'm so impressed. There's so many people here. I'm so impressed. This is really great.
And we are going to give you an honorary membership to the Renaissance Society for here.
Excellent.
I know it's much more valuable than what you're doing, but
oh, I can't wait.
And we're also going to make a monetary contribution to the Seth Nelson Emergency Fund for Students here at the university.
Oh, excellent.
So thank you again.